As an industry, it's critical that we grapple with the technical minutiae of how to build buildings that are fit for the 21st century at a time when humanity's adverse impact on the planet has become so pronounced that many scientists are dubbing it the Anthropocene, a new geological era defined by humanity's destructive effect. But we live in a time when the notion of objective truths is under attack, when political figures can proudly declare that we've had it with experts, and we operate in an industry where sustainability has long been paid lip service, but little more. That's true in the case of the house builder looking to build as cheaply as possible, or the design-led architect who still goes weak-kneed for the steel and glass boxes of oil-age design, or alternatively the postmodern rejection of the idea that there are objective truths, that there are right and wrong ways of building. That's clearly started to change in recent years, what with people waking up to the world being on fire. So events like this matter. I take great heart from the fact that the industry is finally seriously grappling with these issues. And I see that reflected in the fact that a novice event organizer like us has so many people register for our first ever event, and on a subject as technical as thermal breaks. As our first speaker will show, the frustrating thing is that we've known about thermal bridging for a surprisingly long time. So our first speaker is Dr. Mark O'Rian. Mark is a lecturer at the Department of Architecture at Munster Technological University, a director of RUA Architects, and a correspondent with Passive House Plus magazine. He has a PhD in zero energy retrofit and was a leading member of the team to deliver Ireland's first commercial NZEB in 2012. His articles contextualize where low energy design comes from to allow us to understand where we go with it in future. So over to Mark.
Thanks, Dudley, Jeff, and Lenny, and everyone at Passive House magazine. And I'd like to welcome everyone to my talk on the Roundtable webinar. It's going to be on discovering thermal breaks. So without further ado, let's jump right in. Thermal bridging is first referenced in historical literature in a post-war engineering report from the Department of Housing in Denmark in 1956. In a study into moisture transfer in building envelopes, Escold and Korsgaard, who would later go on to design the first zero-energy building in Copenhagen in 1974, found that thermal bridging was happening on the inside of connections between concrete facades and inner floors. They had identified the risk of condensation, particularly with continuous concrete intermediate floor slabs. They also identified that modern, tighter concrete constructions were aggravating the risk of condensation at cold bridges. The report indicates that there was a working knowledge of cold bridging as part of the Scandinavian construction industry prior to the 1950s. Yet, it was probably the language that became a barrier to the broader dissemination of this knowledge around Europe. Prior to the Second World War, human health was a concern of the modernists in particular. We know that Walter Gropius and Maxwell Fry had been arguing that clean modernist buildings improve the living conditions of the people in their Impington project in 1936 in the UK. Pierre Winter, an engineer and neighbour of Corbusier's in Paris, gave a lecture at KIAM 5 in 1937, arguing for a close collaboration between doctors and architects to reduce diseases to a strict minimum. So it was an issue at the time. We also know that Corbusier had understood the importance of aspect and sun path before designing and completing Unité Habation in Marseille in 1952. Many of the young architects in London County Council in 1950 would be heavily influenced by Corbusier's Béton Brut of Unité Habation. In 1953, the LCC London County Council architects completed Winchfield House, which was heavily influenced by Corbusier and Unité de Bastion. In fact, it was James Sterling, who worked with LCC at the time, who attributed the concept of Winchfield House to Corb's much earlier and conceptual City in the Park. Such building designs would not benefit from the understanding of thermal bridging. In fact, it was Marmot in 1978 who argued that Corbusier carried through on a much higher quality in Unité Abbation than LCC did in Winchfield House, where they compromised on so many of the key features of Unité Abbation, which would have benefited the occupiers. Unlike Marseille, London would have a higher risk of condensation with much lower winter temperatures, little in the way of insulation in the buildings. So as we moved through the 1950s and 1960s, would British architecture, who were continuing to provide mass housing, learn from these experiences and gain better understanding of the environmental consequences? As early as 1963, Brown and Wilson, writing in English in the Canadian Building Digest, warned that linear thermal bridges could cause condensation and structural damage, particularly in freeze-thaw conditions, which could be readily overcome with insulation placed over the entire exterior of the building. What a radical idea. They highlighted the impact of lateral heat movement in non-continuous constructions such as timber frame, which were popular in Canada and the US at the time. So as the consequences of thermal bridging becomes more mainstream in the 1960s, would architects and developers of housing and apartments change the way they designed them and built them? Despite the many social and environmental performance failures of the LCC apartment tower buildings through the 1950s and 1960s, still Allison and Peter Smithson would complete another homage to Corbusier nearly 20 years after Winchfield House in 1972 at Robin Hood Gardens. The Smithsons, who we know were environmentally aware, and I would argue that perhaps there was an excuse in 1950s for a lack of knowledge of linear thermal bridging, but was there an excuse in 1972? Realistically, without insulation and with the use of single glazing, thermal bridging must have seemed of little concern in terms of energy loss. In fact, it would be the oil crises of 1973 and 1979 which would bring governments, policy standards, developers, architects, building owners and occupiers to a concern for building energy conservation, and would only be then that issues like thermal bridging would start to get a fair hearing. Although they are all linked, Chernobyl, the Kyoto Protocol, it would be the Energy Performance in Buildings Directive in 2002 that drew our focus into building energy, and we became more concerned about insulation and thereafter thermal bridges in relation to heat loss. So thank you very much for your time today, and I hope this gives you a little bit of historical context to the background of our topic today.
Thanks very much, Mark. That was, as ever, for me, I think, you always provide fascinating historical context, just like with your columns in the magazine. And it is just kind of a sickening feeling to realize how much within our grasp some of this knowledge has been for so long. And it really just gives us even less excuse for our failure to act. Anyway, I'm going to move on to our next speaker now, and I hope, by the way, all of the attendees are enjoying the Pechakucha or Pachakucha, depending on who you're speaking to, format for these presentations, which we're trying to kind of. It's a difficult ask, I know, because when you're dealing with something as technical as thermal bridging, and invariably you kind of have to go into the realms of PowerPoint. So of course, this will not be as seamless as the kind of Pachakucha presentations you'd find on people showing, presentations on I don't know, on what they've had for dinner. But there's more substance hopefully in this, more nutrition intellectually. So our next speaker is Nick Brandt. Nick is one of the, he wouldn't thank me for saying this probably, but he's one of the UK's top passive house consultants. His fingerprints are figuratively and literally all over so many of the most significant sustainable buildings yet built in the UK. Nick trusts in beauty being an emergent property of good design, and subscribes to the view that the best buildings are designed from the inside out, and that engineers are not here to solve the problems arising from the clash between a designer's ego and the laws of nature. So over to you, Nick.
Okay, so this is a thermal bridge, and you can see we've modeled it to look at the heat loss, but that's not what I'm really worried about. I find with thermal bridges, they're actually a symptom of deeper issues. So that's what I'm going to look at here. And I'm talking about new build, not retrofit, which is a different challenge as you'll hear later. So here's a building. It's an old factory building. It's now a luxury flat. The structure is very obvious. It's bricks under compression. There's arches over the windows and so on. No actual thermal bridges here because there's no insulation, but it's a very rational, simple structure. And I could have shown the terrace of Victorian houses. Paint law rights falling water. So here we can see with the invention of reinforced concrete, we can suddenly have a lot of architectural freedom. Again, no thermal bridges because still no insulation. But if we were to insulate this, we can see it would be a lot more difficult than the last example. And here, I mean, you can have some fun Googling cantilevered housing. Extreme architectural expression, clearly lots of challenges here. But is this what we really want to be doing? Are we looking for solutions to this problem? This is an interesting example, clearly very interesting. I think it's very beautiful. It's a potato sorting station, Ukraine. Again, no thermal bridges, but it's definitely cantilevered and it looks structurally challenging, but there's a real rational reason for that layout. If you're going to drive potato lorries underneath it and you don't want any columns to bump into, then this is really a good solution. Now, some housing from 1970s in Camden. This is Stoneleigh Terrace. Original budget 2 million, rose to 9 million. And that's without having to, again, deal with any thermal bridges. If you were to insulate this, then a lot of challenges there if we're trying to achieve air tightness. But just trying to keep the water out was challenge enough. But again, this is the express. So here we've same Camden again. This is a passive house, Chester Balmoor, less extreme than that example, but we've still got some fairly challenging structure. We've got the bricks starting at first floor in places, corner windows. So how do we hold this brickwork up? And the way we do that, of course, is with what you can't see here, is the hidden steel bracketry. So steel angle sections, we see a few under the soffit here. And these have to be thermally broken because they connect the external brickwork to the inner warm structure. And that's expensive, it's difficult. And how do you finish this off underneath? How do you finish the soffit? How do we insulate around these? So lots of technical challenges and things that are quite hard to make look good. Here's a self-build project, 3 thermal breaks outlined here, the location of for a cantilevered balcony. Fairly trivial, you'd think, but the problem is that transferring the load back to the structure needed a lot more steel. You see the middle where we've got masonry meets steel meets timber, a really big challenge for air tightness. So a lot harder than you'd imagine. Easy way to do balconies, support them on posts. This is in Chelmsford, not particularly beautiful. You can see there's big lumps of concrete at the bottom to stop people walking into the posts. So yeah, not lovely, but very cost effective and could be done thermally bridge free. So that ticks those boxes. So maybe a cantilever would be more beautiful. And this is the same development. So yeah, not so beautiful, slightly clunky, introducing more challenging thermal and structural connections. We've got to have thermally broken, even for building regs, you need to thermally break this. And how do you keep the weather out and so on? And the balconies are not very generous here. These are really quite small. Maybe there's a more clever option. Again, same development. Again, not passive house, but this will be insulated. So we can see here there's a lot of challenges for potential thermal bridges, air tightness details, weather tightness. And again, to my mind, this isn't looking beautiful. We've got silly little bits of brick. This isn't freedom of expression. This is just a not very well thought through design. In Freiburg, so here we've got, you can hardly see it in the background, there's just these nice balcony details. It's galvanized steel, it's all pretty industrial and pretty basic, but the overall effect is really lovely. We've got nice plantings, there's nice furniture, a really nice vibe in the cafe here. Just very, the overall effect's very good. And also Freiburg, some housing. The very generous balcony spaces. We've got a lot of space here, supported on columns, quite nicely proportioned. Very simple balustrades without using toughened glass and so on. So thermally broken. This is part of the Passive House development in Freiburg. Slightly more complicated again in Freiburg. Here the balconies cantilever out a bit further to give a bit more space and a bit of change in expression, but quite simple to do because it's beyond the thermal envelope again. So these are, although they're cantilevering beyond the posts, this is all outside the envelope, so it's not really that challenging. And again, very generous spaces, looks really nice. Agale Grove in Camden again, so this followed on from Chester Balmore. The balconies here are supported as Freiburg on external structure. Looks a bit different, but really quite a rational structure there, and less thermal bridging meant thinner insulation than Chester Balmore, so a 200mm insulation of the cavities rather than 300. But this is a canopy at the entrance. Doesn't look much of a problem, but it's quite a cantilever. That created quite a challenge for thermal bridges, air tightness, and so on. And doesn't even give you any protection as you come in. So is that really the most clever design solution? It creates a lot of challenges, but could we have had an easier solution that was easier to build and function just as well? So this could be a development anywhere. This is some housing in Gloucester. Classic thing of lightweight cladding, external insulation, and then fixed back to either masonry or steel structure. And here we can't avoid the thermal bridging. We need something to connect the two together, which goes through the insulation. And the usual solution is aluminium brackets, which is quite a hemorrhages heat. And they're thermally broken ones are expensive. Here, Monty Paulson in Canada has just used stainless steel screws, difficult to prove structurally, so they actually mocked it up and tested it out. So it's a nice simple solution to a challenging problem. So in summary, if possible, design out thermal bridges. So yeah, don't create structurally challenging situations like cantilever balconies and so on. Try and design these out because that'll create savings. It'll potentially even look more beautiful. And where it's unavoidable, so where we've got to connect to the ground with foundations, or if we're wanting to hang lightweight facades off the structure, then we do need some thermally broken connectors. But what we need here is low-cost, simple connectors that everyone can use, not just for Passive House projects. We need that everything you can get from the builder's merchant is thermally broken, so we're not wasting energy and creating potential mold and moisture problems, as other speakers will talk about. Thanks very much for your time.
Thank you very much, Nick. No, you did a great job, and apologies from my end, everyone, as well. The idea of this of stumbling through a present organization event like this might seem a lot more charming in reality, you know, in principle than the actual reality is, you know. So apologies. Our final speaker in the first session is Sarah Price, Dr. Sarah Price, Director of Building Physics and Consultancy at Inhabit. Sarah has experience of working on a wide variety of projects related to energy in the built environment, from concept through to commissioning. She's a specialist in the technical performance in buildings, including thermal bridge analysis, energy modeling, air tightness, moisture, ventilation, and she has a deep understanding of the relationship between different building performance standards in the UK, from building regulations to Passive House. She's currently the technical author for PAS 2035, the new overarching document in the UK, the Retrofit Standards Framework, introduced following the recommendations of the Each Home Counts Review. And she's co-author of the Retrofit Coordinator Qualification, an AECB trustee, and an AECB expert advisor. So over to you, Sarah.
Thank you very much. I'm from Inhabit, and we're consultants and engineers, and we specialise in low energy buildings and building performance. I'm a building physicist, as Jeff has said, and I'm passionate about our planet, and I have a YouTube channel called Climate Change Starts at Home. So if you want any top tips about retrofitting, that's the place to go. So I'm going to mainly talk about thermal bridges and retrofit today, because they're trickier to deal with and they're more prevalent, and we'll have them. And this is my cat, Scully, and I put her there because she loves warm places and she hates cold bridges. She's sitting on my husband's laptop there because it's the warmest place to be. So a bit of context, what we do now is we might install loft insulation, a boiler, new windows, but there's no joined up thinking. We do step-by-step retrofits, but there's no design, there's no planning. We don't think about the junctions, the corners and the edges, and we don't think about how the insulation's impacting on heating and ventilation. So we end up with unintended consequences like this one. And that's not just mold growth. So there's loads of unintended consequences like increased energy bills or fire or poor indoor air quality or degradation of the structure. This is just one of them. A lot of them related to moisture. Can we have a thermal bridge free retrofit, or is it an oxymoron? Well, if we say thermal bridging is continuous insulation all the way around a building, then no, we can't, but we can mitigate against them. And there's two main issues with thermal bridges: mold growth and heat loss. So here's an example of external wall insulation. On the left-hand side, we've got the external wall insulation finishing just above the ground level. So both these properties have got solid floors in them. On the right-hand side, this is an inhabit one, and we've got external wall insulation extending down below ground level. So it's just the foundation that's in there. And then these are building physics models of those thermal bridges. And we can see the internal surface temperature that might occur at different internal and external temperatures. And you can see the one where the insulation doesn't come down as far on the left is a much colder internal surface temperature than the one on the right. But I've got thermal bridges. We've all got thermal bridges, and some are fine, like my wall to floor junction, and some are not fine. Some are mouldy, like my in my bay window here. So I've got nice black mold growth that I have to clean off every year. So why is that? It's not as straightforward as if you've got a thermal bridge, you get mold growth. We need to manage the risks. So we need to make sure that the space is heated well. We need to make sure that it's ventilated well and into the corners. That's the really difficult bit. We've got to try and control moisture. So through cooking, washing, bathing, we've got to make sure that we remove that excess moisture from the home. There's another definition of thermal bridges, not just continuous insulation or incontinuous insulation, as the case might be, but it's actually a mathematical correction factor for a heat loss calculation. So we have U values that deal with the plane elements, and we have psi values that deal with the corners. And they come in all shapes and sizes, good, bad, and ugly. So we can have good thermal bridges that actually make the heat loss better, because you basically said that that corner is not providing excess heat loss. We can have bad thermal bridges, most of them are, that mean that we do get more heat loss. And then we have ugly ones as well. So how much heat can a thermal bridge lose? Well, we've got this situation where we're going to keep the windows in the concrete layer, big psi value, 0.5 watts per meter Kelvin. If we move the windows out into the insulation layer, we haven't installed it there yet, we get a really tiny psi value. But what does that actually mean? Well, if we leave the windows in the concrete, that's equivalent to 500 watts of heat loss, or having a Hoover on all the time in the winter. If you keep them in the insulation or move them to the insulation layer, it's the same as charging a smartphone. So 5 watts, much smaller heat loss. Cladding fixings, Nick talked about cladding fixings. So I have a bee in my bonnet about cladding fixings. So this is an aluminium fixing. It increases the heat loss in the insulation by 92%. And these calculations were done by Green Gauge. They're 3D thermal bridge calculations. And they worked out how many of these cladding fixings we needed. If we take a bit of foam glass and we put that, so that's a structural insulating block, 50 mil of it, put that between the wall and the fixing, we still increase heat loss by 42%. So huge amount of heat loss. What we really need to do is we need to have a look at the material that it's made out of. So this cladding fixing is made of protruded GRP, or fiberglass, as you might know it, and it increases the heat loss by only 8%. So it's exactly the same size and shape, but it's made of a different material. So it's all about the materials here. If we take something like aluminium, it's got a massive thermal conductivity, which means it loves transferring heat. So 200 watts per meter Kelvin. Steel, bit better, 50, stainless steel at 17, but GRP 0.35. And our insulating materials are about 0.03. You can see on the left here, it looks like aluminium actually, but it's a lot better performing. Let's have a look at balcony connectors, another thing Nick mentioned. So here we've got some steel to steel thermal broken balcony connectors. Okay, so these are designed to break the connection between steel to steel. But what we find is that actually they're still quite big thermal bridges. If you've got a decent amount of insulation in there, you put one of those in, it's still a thermal bridge. And this project has got 23 balcony connectors in it, and that makes 4% of all the heat loss from the building. So it's still quite significant. They add up very, very quickly if you look at the heat losses. So in summary, manage the risks of your thermal bridges, remove the moisture, get your ventilation right, make sure your buildings are heated well, understand the heat losses. So how much is it actually going to cost you? Are you going for certification? Does it really matter? And lastly, don't use metal. Think about the materials that you're going to be using. And that's me done.
Thanks very much, Sarah. That was very interesting. And you found a way to put some quite technical subject matter across in terms that at least I could understand, so I think everyone else's chances must be good. What we're going to do now is open it up for a panel discussion we're in the region of about 20 minutes or so. The top one, which I guess we'll deal with, is what is the best way to thermally break a window that is fixed back to SFS? I presume that's a steel frame structure, and sealed around the frame to metal angles at the sill and head.
Don't do it. You need to put something, well, try and avoid using steel angles for a start. But if you have to use steel angles, you could put something like compact foam between, which is a structural insulating material between the steel angle and the window frame. You can do it using, in a retrofit situation, we use timber bearer underneath, simple solution, steel straps going back at points, which is very small thermal bridges, and so therefore you're reducing the heat loss.
Very good. I should say as well that thank you for that, but I preempted myself a little bit. I'm going to actually introduce some of the panel speakers. But anyway, John Moorhead. John is the managing director of Wayne Moorhead Architects. He's a long-standing interest and involvement in low energy building. John became a certified passive house designer in 2010 and has produced a number of landmark architectural passive house projects ever since. Buildings that I would describe them as wearing both polo necks and anoraks, you might say. In other words, they satisfy the architect and the building physicist alike. And I should say the anorak is a badge of honor in my book as well. But I think it's that rare combination which is very powerful. So it's something we always look for in the magazine. Then our next panelist, Tara Fraser. Tara is a chartered structural and civil engineer and director of Build Collective, who enjoys working with architects and contractors. She enjoys the challenge of creativity and practicality that we all try and balance out in the design of buildings. Under Tara's leadership, Build Collective are a rare beast, I would say, a structural engineering firm who are operating at the leading edge of energy performance, material sustainability and structure. We've Robert White, or Rob. He's a technical associate at Archetype, arguably one of the leading sustainable architectural practices in the world over the last decade or so. Rob drives forward the practice's technical approach to architecture using research, post-occupancy evaluation to inform the design and delivery of some of the UK's biggest passive house plus buildings, including one. I remember Lloyd Altra, the managing editor of treehugger.com, describing one of their projects, the UEA Enterprise Centre, as being a building that was almost edible. The components in it were so kind of virtuous. Ruth Butler is an architect and registered REBA client advisor. She specialises in contemporary low-carbon environments for sensitive refurbishments and new builds. She lives in her own self-built Hampshire passive house on the south coast of England and is currently a Passive House Trust Awards finalist for her New Forest Enerfit project. Her projects have been published, exhibited and broadcast. We've David Stevenson. David is a qualified domestic energy assessor, retrofit coordinator and level 1 airtightness tester. David's an energy officer within the housing investment team of Renfrewshire Council. Renfrewshire have adopted and have been implementing a past 2035 compliant whole house fabric first approach for the last few years, adapted to suit social housing. This approach is intended to drive down energy demand and in turn lower carbon emissions and fuel bills to make both tenancies and the housing stock sustainable in the coming years. And I just think Renfrewshire have extraordinary insight from a client's perspective of what can go wrong when you have vulnerable people in underheated buildings where you can have significant moisture risks, which is fantastic work they're doing. Our panel also includes a building contractor, product supplier, and 2 more academics. Rafael De La Mata of Bowtie Construction, Chris Lister of Farrat, and Professor Will Swan and Joe Pemberton of the University of Salford, who I'll introduce more fully before their presentations in the second half. But we'll launch back into the roundtable discussion now. Unless I guess we'll move on to the next question. There's another kind of technical question here: how best to deal with thermal bridging when upgrading and retrofitting an existing house, such as a 1980s cavity wall with reinforced concrete ring beam under the wall plate?
Jeff, just firstly, I think it might be worth going back to the previous question and not to be myopic, like we could accuse our predecessors back before the 60s in that they didn't look at thermal bridging. Fire is a big issue, and fixing windows back into steel frame structures needs to take that account seriously. And I think that's an area that we need to get industry to have a very serious look at, so we can get more products out into the market that will enable us to not forget fire. Like, you know, we can be obsessed with thermal and forget about moisture ingress from wind-driven rain, etc. And then our thermal doesn't work. Our thermal doesn't work either if it fails, of course, in a fire. On retrofitting, obviously with concrete ring beam, external insulation is really the way to go. I have one in my own place, 1965 flat roof box, beautiful ring beam, classic thermal bridge, great for checking your infrared cameras operating correctly. And really the best way is to attack it from the outside, in my view.
If I could just broaden it out for a second as well, we'll come back to the questions as well. John, I'd love to know where you sit. You're, I think, a good example. I know you and Nick are good friends as well, you've got a very interesting perspective on, you know, you produce the kinds of buildings that I suppose go against, to some extent, the preconceived notions people may have about what, like, the likes of a passive house can look like. You know, about the extent of the glazing or the overhangs, you know, balconies and so on. And I just wonder, you know, where do we sit? On one hand, we could have, and I'd love to Nick's perspective on this as well. You know, the purity and the simplicity and of a box, you know, which can still look beautiful, of course, with quite sober glazing ratios and so on. And then on the other hand, we have, you know, the kind of glass and steel box. You know, where do we sit? What are the right kinds of solutions, do we think? Can we take kind of dogmatic approaches to this, or you know, extreme positions on this, or what should we be doing, really?
I think we mustn't lose sight of the fact what the buildings are for. They're generally for human occupation. They're not, you know, okay, it's been argued many a time, I think, that you know, putting thermostats in buildings might monitor the energy use of the building, but has very little to do with the comfort of the occupant. So I think that's the first thing to look at. And I think our buildings, we haven't had to change our building design because of adopting Passive House as a strategy, I would say. In fact, our first Passive House was already on site before we knew about Passive House and was able to get certified without any changes, really. That said, the whole Passive House thing would have educated the finesse of thermal bridge eradication, etc., during the build. But I don't think the two need to be, you know, pushing each other apart. I think they can be embraced. I think they need to be, you know, I think multidisciplinary input early on is very important. And I think that's where the architect needs to embrace other people's knowledge in industry and not sort of siloize themselves in their mentality. I mean, I saw one of the speakers there referring to, and in fact it was Mark, talking about how things changed in 2002. I know we had to review a building that was built with diaphragm construction, and it was built in 2005 with insulation, only on in the cavity area, which was about a 900 mil cavity. So fundamentally, that was flawed. That was architectural expression that had been picked up from the 40s and was being driven home too far and wasn't fit for purpose. And then you end up with what Nick was identifying, all these bolt-ons and bits to try to resolve the problems. I think if they're caught early, you don't end up in that corner, and you can enjoy those big views with big glass walls facing the wrong way, maybe from a solar perspective, but can be compensated for. You know, I think if you can get your heat loads down, you can distribute your comfort levels within the building quite well, without being a slave to, you know, form factors and maths dictating things. But that would be my view.
I'd agree with John there, you know, from the context of, you know, what Sarah was saying as well, that we can design buildings to suit people, and we can design new buildings, you know, to be thermally bridge free. Equally, we can take existing buildings. Now, it may mean that we have to go to a deeper level of retrofit and taking out intermediate floors, or taking out the ceiling to the cold attic in order to achieve that. But maybe that's what's needed to give a building another 50 years of lifespan. You know, and I think that's where we undervalue what we're doing in construction when we're talking about retrofit. We're forgetting that many of the materials that are in the buildings are far beyond their designed lifespan. So when we go to deep retrofit, what we need to consider is a far more systemic approach to minimizing the threats of thermal bridging, and definitely in most cases it's going to be external insulation is going to mitigate that as much as possible, and then you're looking at your connections.
Is the issue that I just something that occurs to me is part of the problem, and I'll put this to you perhaps, Nick, that designers go into designing low energy buildings without, in some cases, without understanding the risks and consequences from a thermal bridging perspective. In other words, if you know that if they were, and to extend that, if they were to be made aware early on of the consequences, whether it's you know just in terms of complexity, in terms of cost, and so on, of needing to kind of to really go to town on solving thermal bridging after the initial design. Do you think that it's something that designers will tend to learn from once it's been brought to their attention, or do the eyes remain glazed over?
I think you've got to learn the lesson the hard way. I mean, as architects, we've worked with over many buildings, and it's almost sometimes you spot something, you think, I bet that's going to be difficult, but you kind of can't prove it, or I bet that's going to be expensive. And it's only when it's built, and oh shit, you know, it's something just having windows all different sizes. The QA, it doesn't cost any more, but if you pick the wrong one off the stillage, you go up the thing, go to put it in, it's slightly wrong. You know, in extremes, you end up people adjusting the opening because they think, oh, it must be opening wrong. Then they come and get the next window, think, oh shit, no, it's just the wrong window. Those sort of things, how do you cost that? So, but once you've made that mistake once, then you think, right, we won't do that again. And it's kind of hard. So a lot of these things, it's just hard experience. And if you've got the same, what's great is you've got the same team. We work with archetype a lot, and often the same engineers and the same M&E, and it becomes much easier because you can all say, oh yeah, no, we did that before, we're not going to do that again. But it's very hard when you're with a new team to sort of bring that hunch in. You say, well, actually, I think, and everyone will argue if they're really holding on to this idea that no, it won't cost any more, and we've got to fix for it, we can just use this clever connector and that'll be fine. And you kind of think, yeah, but I bet there's a problem, and you get to the air tightness and then the problems start. So I think again, this is a simplicity thing. And I think the thing with design, it's a shame. I'm really sorry that I put it's all my fault with the technical thing. I did address this a bit in the presentation. So this idea of architectural expression, and sure you can fix stuff, but there's a approach to design where you're working from the inside out, and then you kind of trust that the beauty will emerge from that. And there's quite a leap of faith with that, because there's a bit where you are just sorting out the bed spaces and the daylighting ratio, daylight impact stuff, and you haven't got beautiful architecture yet. The other extreme, which we have worked with people who the first thing is to do the 3D render. You haven't even thought how it's going to hold up or where the structure is, but you do literally do a beautiful 3D render with people in it. And they're the sort of two extremes. And most people are working somewhere in the middle, a bit of considering how it's built and a bit of thinking what it looks like. But I kind of put up a big thing for trying to really think from the inside out and trusting, because a lot of vernacular architecture, which we tend to, it's the one type of architecture everyone kind of loves, whether it's architects or just the general public or a Daily Mail reader. Apologies to Daily Mail readers who are watching. But they come out of people just solving problems, often with no actual learned design skills and very limited palette of materials. And some of it's a bit wacky and quirky, but generally, it hits more than it misses. But yeah, so it's a big topic.
Just to jump in there to build on what Nick has just said, our experience, as I suppose, of a practice in archetype, is the earliest you can get collaboration from other consultants, engineers, QSs, even bringing in the contractors early can, as we say quite a bit, is de-risk the unknowns as early as possible. The worst thing you want to do is go along all the way up to stage 3 past planning. Then you realize, oh, here we go, we have a whole lot of thermal bricks, and how are we going to shoehorn them in? We're literally from stage 0, inception of project, they're the sort of things you need to look at. How do we eliminate them, simplify, and especially when it comes to regional context and materiality, specifying materials that are attainable and appropriate to the location, and actually the understanding of the materials and the capabilities of each material is very important. I think, which Sarah showed, the difference between steel, stainless steel, and aluminium, can all kind of look the same on the outside, but can have quite significant effect on your heat loss and potentially condensation risk. So yeah.
Tara, I'd be interested in your perspective as a structural engineer, because not to be impolite about structural engineers, but they've been generally, from my experience, they've been quite late to the party, and they tend to be quite defensive, conservative, I suppose, because their primary consideration is about ensuring that the building doesn't fall down, right?
Yeah, absolutely.
But
it's a basic level thing, isn't it?
Yeah, but to me it feels like, for years, the term that occurs to me is that the industry has been practicing what I call kind of dumb empiricism. In other words, we build things a certain way, and the ones that don't catch fire or don't collapse are the ones we keep on building. We don't maybe know why exactly they didn't catch fire, didn't collapse, but we don't ask too many questions. It feels like there's too much of a disconnect. But how do you, as a structural engineer, reconcile these things in a way that you're not just paying lip service, and that way that you're when I saw Beth Williams, for instance, talking about concrete-free foundations, for instance, I mean,
yeah.
The very concept of a structural engineer talking about that, to me, I think is extraordinary, and laudable, I should say. But, where do you see it from a structural engineer's perspective?
We've got to change, haven't we? I mean, we're very codified. So we've got all these British standards, Eurocodes, and we've got to think about where our PI insurance is. It's in some reality, because if something goes wrong, that's where it is. But we've also got to look back in the past, because some of our, like concrete-free foundations, if you look back in the past, we didn't use concrete in foundations. And so it's kind of looking back in the past to see what happens there. And that's kind of where that's kind of come about. And we've got clients that want to push us as well, and they don't want concrete. And so we've done put a bit of effort into it, if you like, and and some of that depends on the ground conditions. So a lot of these things for us, ground conditions are really important. 9 times out of 10, our structures are going to have raft foundations to get the best thermal performance out to the ground. Yeah, to minimize that risk. And the other thing we've got is, we've got to think about who's going to be building it at the end of the day, and where we are in the UK and what skill sets are available. Because there's no point in us doing a timber frame house in an area where all the builders are doing masonry. Yeah,
absolutely.
And so we just had a recently one where someone wanted to do timber panels. The builders around there are all masonry. So we're going to go to poriform block, 365 poriform block, insulation, and then the stonework on the outside. Okay, it's a 600 mil build up, but we're in the middle of the countryside. No one sees that build up, and you get the U values you need. Yeah. So it's just kind of, and what we try and do is, we get a lot of people saying, oh, our fees are expensive, or why we're doing 2 stages. But the 2 stages are so we can have that communication.
Yeah, we can have those early ideas and work through them rather than, well, here's just, because I think what I hear a lot is the engineer just hands out a solution to the architect and it gets incorporated into drawings.
Absolutely.
Yeah.
Ruth, I'd like to bring you in as well. We'll maybe have a little bit more discussion just for a couple of minutes, and then we'll head back into Raphael. Will be presenting next. Ruth, you know, you strike me as someone who's very well plugged into the architectural establishment, and I'd love to know your thoughts on because there has been a sense, a meaningful sense within the last year or so of real movement, whether it's within the institute, whether it's movements like Letty, for instance, you know, and Architects Clare and so on. What's your sense? Do you think that your peers, your colleagues, are actually starting to take this stuff seriously now?
Yeah, I think it's looking from the inside out, as it were, and I work a fair bit with the RIBA as well. There is a growing body of expertise, and it's gone from being a few sort of leading lights taking an interest to it being a much wider sense of interest from the whole profession. And I think the argument's been won. Everyone is behind the cause, as it were. And the question now is, how do we do it? That's the question that everybody's asking, not should we do it, or even so much issues of cost really are less discussed, they're still on the table. But the gap between building a passive house and if you're building a new build or building to what you might call building regulations, that gap is down to less than 10%. Some would argue it's down to 0. Some say it hovers around 5%. Doesn't really matter, it's a very small number. So I think we've won that argument. And as an architect who's built inhabits and passive houses and all sorts, I think once you're there, it's impossible to go back. So you just have to get more and more people there and keep bringing that price down, because you know, you can't walk down the street. I can't walk down the street any longer without playing Spot the Thermal Bridge. Or it's ruined my life building to passive house standard, really. It's impossible to go backwards ever. So and now, and I think that's the case for anybody that's been there, and it's just a matter of convincing enough people to keep marching on, really.
All the more reason why it's important that rather than architects just, for instance, getting specialists in to assist them, you know, with subjects. And of course, those consultants will be important, but that they actually engage themselves. So they can't just say that they silo off the fact that here's our passive house project, we did the design, but we allowed the boffins to sort out the technical details for us. You know, so that they learn from that. Fine, I just want to bring David in quickly before we move on to Raphael. David, I mean, I just fascinated to know because of the monitoring work that you've been doing on retrofits that Renfrewshire have done over the last years, and the issues that you've been describing. I remember Duncan Smith, your colleague, talking to me about a dashboard system for, you know, a kind of condensation and mold monitoring system that the council has, where you've got a days till mold occurs, you know, sort of timeline occurring. But David, to what extent would you say that thermal bridging has been a factor in some of the issues that Renfrewshire has experienced?
It definitely has, and I think it's more about the unintended consequences, I guess, of retrofit that you would see more than anything else. But it's exacerbated by the fact it's fuel poverty. So going back to what Sarah was saying, it's about heating and ventilation and almost trying to manage the risks. And I think certainly on the back of COVID as well, people are spending more time in the house, or have spent more time in the house, and that's typical of I know I'm being broad here, but it's typical of a social housing tenant spending most of their time in the house, potentially not heating, not ventilating. And obviously that's exacerbated in areas of thermal bridges. But what we're trying to do is address that, and we don't find a lot of these issues until a house is handed back to us, because tenants generally don't engage with us because they're embarrassed of damp and mold and condensation, because they can't afford to heat the houses and things like that. So the dashboard and the sensors that we've got gives us insight into what's going on, and we can almost get to engage with tenants before it becomes an issue. So we can go and offer help. We can go and say, look, is there an issue why you're not heating the house, or you're not being able to ventilate? Is it a financial thing? Is there assistance we can help with? Do you need to switch your energy supplier? We can help with that. Is there any grant funding you're available for? Is it just an education of how to use your heating system, use your ventilation, open windows, these kind of things? But we're starting to get to the point where when we're doing retrofit works, that we are addressing all the bridges, or we're trying to address all the bridges, and hopefully that's going to start to mitigate the risks moving forward.
That's fascinating. I mean, it raises the question that there are particular kinds of occupancy types and profiles, perhaps, where where there's greater stress is being placed on buildings. So you're talking about cases, if I understand correctly, where some people are on income of £5,000 to £6,000 a year. It's not fuel poverty; it's poverty. So in other words, from a policy perspective, it's almost as if these are the places where these are the canaries in the coal mine, for want of a better term, and perhaps these are the situations where I mean, we should be addressing these issues across the board, but these cases where you've got people, vulnerable people and low income. On low incomes should be surely the priority to try and to try and give them a living environment that is unlikely, however they choose or however they're able to live in the building or to heat the building, so that it's unlikely to cause problems. Because the problem, of course, then is not just for the occupant; it's for the landlord in the context of increased repair and replacement and so on, right, arising from the damage.
Yeah, absolutely. I mean, as I said, we sometimes don't, or most of the time, don't find out about the issues that are potentially there until the house is handed back to us, and then at that point you could be left with 10-15 grand's worth of damage or repairs that need to be done to bring the house back up to that livable standard. And you can understand if people are on low income and they're embarrassed because there's these issues happening in the house. So the sensors that we're installing allow us to kind of try and get ahead of that. So we're not only protecting the asset, so reducing our costs, which we can then spend somewhere else, potentially on retrofit works to help other people, but we're also hopefully helping the tenants to get help that they need. And whether it's a referral to someone that can help with money, whether it's a health issue, whether it's a social issue, we normally wouldn't know, but hopefully this will start to open things up and allow us to see what's going on and try to engage more.
I just think it's extraordinary. I think Rent for sure needs to be applauded for their leadership in this regard, and we need to see more councils, more landlords following suit. We'll get more deeply into the Q&A in the second session, but I want to we're running a little bit over time, so I want to get launch into the second set of presentations. So the next speaker up is Rafael Delamata. Rafael, am I pronouncing your surname correctly, by the way, or not?
That is correct.
Okay, it's basic common courtesy to try and get right. Rafael is the technical director of Bowtie Construction, London's leading passive house builders. A man who had the audacity to attempt to build part of a passive house out of Lego, as I found out when editing the Passive House Plus article on legendary engineer Max Fordham's passive house. He supervises low to zero energy construction projects in the range of £800,000 to £4 million, and he's got invaluable insights to share now from the perspective of the builder, an informed builder, albeit, but nonetheless a builder.
Yes, and I started working on the much smaller projects, just so everyone knows. We started doing extension, loft conversions, and then we moved on to the larger projects. But that's great. Thank you for introduction. Good morning, everyone. My name is Rafael. I'm a technical director for Bowtie Construction and also very keen mechanical engineer. and my job is mainly to improve the project's design as early as possible before we move ahead with the construction. And today I want to talk about thermal breaks and a few considerations, like, have thermal breaks been designed on the project? Have they been included in the costing documentation? Are they causing us additional costs and not only costs for fabrication, but also lost time? And do we have other problems or solutions? So we're going to talk about a few examples. This is one of our recent new build passive house projects, which has been complete, which has a very complicated and very extensive steel frame. The focus here will be on a thermal break between the brise-soleil and steel structure. So no wall has been parallel in that building, which created us a mass amount of problems with the steel structure. And we had to build the entire project in 3D photo on the left. So it's a rapid coordination between our steel supplier, Stilo, which produces IFC files, and also Contrasol, which is a supplier of the brise-soleils. What we're basically trying to show is that the thermal break issue, which we had, was extremely complicated to coordinate between various parties. And the lessons from this was that we're trying now to avoid the situations in which we have two contractors divided by a thermal break. We heavily underestimate the amount of time that we required to coordinate both subcontractors, and the steel frame was constructed from the 3D model, but all the columns, which you can see on the left-hand side photograph, been positioned using a total station and a professional surveying engineer. And after steel structure was assembled, we carried further checks, again, to make sure that the thermal breaks are in the right positions. We used here a Farrat thermal breaks. It's a simple sandwich, and air tightness test was used between steel plates and plywood structure with airtight silicone around all the bolts. So that was ready for the specialist contractor Contrasol to come in and fit the brackets. You can see that the arms sticking out on the left-hand side, and then further fins being added on. This was followed by installation of the zinc cladding all the way around the building. And it was very successful. We completed the coordination, including very random angles on this brise-soleil system. And I think few things now to summarize from this project. Because we're working on a essentially thermal bridge-free passive house, but those elements have not been designed out. And even though we had separate pricing in a document, it wasn't enough. And did we allow additional costs and time for all this work? The answer was no, we didn't. And a further complication was that we had to position thermal breaks in consideration of air tightness, and also the size of thermal breaks changed due to the shading wind loads. So the next project is a Patney inhabit project, quite a simple build. Again, externally insulated from outside, 200 mil of insulation wrapping the whole building, so that wasn't too many thermal breaks. But we had 3D model all the steel connections as per structural engineer specifications and our site survey. We then asked the steel supplier to add our standard thermal break sandwich. So this is something we just using now as a standard. It's a 2 pieces of 300 by 300 by 10 mil plates with 4 number of M16 bolts and 25 mil Farrat TBK thermal break in between. And that's when we haven't got the design ready by engineer or architect, we simply put that in and we know it will work. We then follow this with the structural engineer and double check everything. And then the thermal break will only be used on this project for the columns. So all the other walls will be externally cladded, so we don't need any thermal breaks. And the project was delayed by 1 week because of the delay on coordination of those plates. So have we had the thermal breaks designed? No, and there was a separately price, which was good. And I think this was correctly costed, but no extra time was allowed for the fact that the thermal breaks have to be done to measure. And then our next is a Kentish Town inhabit project, which required complete internal demolition. So very deep retrofit. New internal timber structure was built and it was connected with the old shell of the building. On that project, we worked with Bob Johnson, the structural engineer, who was fully aware of thermal bridging, which was very great news for us. We really like his approach and hope for more engineers to adopt this simple technique where the cold steel is marked blue, the hot steel is marked red. So when the question is, do we have the thermal breaks designed? Yes, and this was one of the very few projects that was properly done. Did we have that costed in? Yes, and it was properly costed. There was no additional cost later on, no delays, all went very smooth. And the color coding also helped laborers on site understanding which parts of the steel structure have to be additionally insulated. So that was me. Thank you very much. And thank you for the opportunity to speak today. And I apologize if this was extremely a practical approach and concentrating purely on steel connections. But I thought if I give you some realistic examples, dive into one detail, we're not going to be talking only about very vague ideas of the thermal break.
I think it's very useful, Raphael. I mean, even that takeaway of the color coding, it's analogous to the way that you know, it's become quite common to have the airtight layer drawn in red on the plans. You know, so that people, so that there's just more visual recognition of what it is. So I think that's a great takeaway. So next up, this is Professor Will Swan, is the Director of Energy House Laboratories at the University of Salford, where he leads the Buildings and Energy Research and Innovation team. He's currently leading the development of the £16 million Energy House 2.0 project, a major building performance research facility. He's also chair of the Greater Manchester Combined Authority Low Carbon Buildings Challenge Group and a member of the mayoral Retrofit Task Force. And Joe Pemberton, who's chairing this presentation with him, studied mechanical engineering, finding aptitudes in heat transfer and fluid mechanics before taking up an Industrial Cooperative Awards in Science and Technology, PhD, to further his studies into heat transfer, applying the physics to real industrial applications. Jointly working with Farrat and Energy House Laboratories at the University of Salford, the work focuses on the design of an experiment to quantify thermal bridging and structural breaks with modelling and in situ measurements.
Okay, Joe.
Right, excellent. Yeah, so thanks for the introduction. As you say, I'm the iCase candidate, which is a forefront in the joint project between Farrat and the University of Salford. So Farrat have invested in the project due to this gap in knowledge, because there seems to be a lack of measurement methods to quantify the type of structural thermal break that Raphael was just mentioning. The quantification of these bridges solely relies on modelling, so you can see that huge performance gap issues could arise if modelling is just relied upon. So if Will covers the next background to the project.
Okay, so this is really the background to the project. Is what we're involved with at Energy House Labs is very much around housing, and it's starting with this policy imperative of getting to zero. But what we've been talking about is, you know, it's not just that, it's hydrothermal, it's comfort, it's affordability, it's design. So, you know, a very simple policy imperative can lead to all sorts of unintended and intended consequences. Next slide, please, Joe. And this is really what we do. So we measure things. So we have 3 labs in existence, and also Energy House 2 that you can see behind me, which is currently under construction, due for early next year. So Energy House 1 is a Victorian end terrace in a climate controlled lab, and we use that for retrofit. We're retrofitting it and re-retrofitting it for a major project for bays at the moment, looking at the impact of different types of technologies, but also some innovations. Thermal measurement laboratory, which is really looking at insulation and the performance of heat transfer, and smart meters and smart homes, because actually that kind of measurement is part of what we're all about. So, you know, when Farrat came to us, that was really where they came to us, to find somebody to find a way to actually measure rather than just model what's going on with thermal bridges. So I'll pass to Joe.
Right, so really what my job is to investigate the thermal characteristics around this nuanced thermal bridge and the break solution using modeling and measurement techniques. We need to do this because there's no current standardized measurement method because of the complex heat flows. Yeah, the increase in heat loss is obvious, we all know this, and the detriments to the occupancy and the building health are also present, as we all know. And balconies are becoming more and more popular, so this needs to be addressed. And the reason and how I'm going to do this is to develop an experimental design geared at the quantification of these thermal bridges in situ. I mean, specifically the structural thermal bridging, which Raphael just mentioned, and the breaks and the impacts that the breaks have, hopefully to promote the uptake and boost the knowledge and understanding to increase design freedom for the architects. This is the test facility that Will just mentioned. It's a well-instrumented test facility. It's a pre-1920s Victorian end terrace. When it was built, it was representative of around 20% of the UK housing stock. But it's importantly, it was built inside a climatic chamber, which is capable of producing -5 and +30 degrees temperature dynamically, or it can hold these temperatures to quasi-steady state, which allows me to it provides a unique opportunity really to validate theory and novel measurements, which is exactly what I did in a preliminary experiment analyzing a simple corner bridge. And I used 2 novel measurement methods, one with IRT and one with heat flux plates. So the bottom image there, you can see the test setup array. The high emissivity tape is where I aimed each camera at, looking at parallel to each wall, and the heat flux array you can see. This deduced I took measurements from this investigative detail to calibrate a thermal model to try and validate the model calibration technique for the experimental design. Surface resistances were set at standardized values, and we found that the learnings from this is that the actual surface resistance values you set are quite sensitive. So the standardized versions of the surface resistance are set, were taken forward to the next experiment and measured. This is an infrared image reconstructed in the CSV file. So you can see the little markings that I've made there every 10 mil away from the thermal bridge. And you can see how the temperature drops as you reach the thermal bridge. Now, this is how we calculated the incident factor, and I did it with the heat flux meter and the infrared. I converted them to psi values and compared them to the finite element simulation, and I found a really good agreement. So this was then carried on into the next experiment where we could really look into the 3D heat flows. So this 3D experiment was a preliminary one. It's a little bit like a Juliet balcony, as we've seen before, but we had to modify the Energy House to produce this balcony, to produce this thermal bridge, because there was no 3D bridges of this sort where we could test thermal breaks. So we realized this by putting a steel cantilever beam on. We had to make a soft sand cement mix to try and make perfect thermal contact because the brick surface was quite rough. You can see preliminary infrared imaging on the right hand side there shows a cold spot on the internal face, and the sensor array on the left hand side is what I used to tune the model to try and calibrate the model. This is the model comparison with and without the break with this initial test phase, and we found a very small saving of about 5%, because this isn't really where these thermal breaks should be positioned. They shouldn't be butted up straight against a wall. They should be sort of in the middle of the insulation layer. So we saw a really small effect. So I had to try and modify the test. And what I did is I retrofitted external wall insulation around the thermal bridge to try and exacerbate the thermal bridge effect. Now, I didn't know what thickness this external wall insulation would be because it's comprised of soft wool. So I didn't know what thickness it was going to be when it was retrofitted to the wall. So I used a heat flow meter to compress it at different thicknesses and found an effective conductivity at each thickness. So when it was retrofitted, I could just interpolate the actual effective conductivity and then input that into the model, which is what I did here. And you can see the comparison. Now, if you look at the table on the right-hand side, phase 1 was without a break and phase 4 was also without a break. But phase 4 had external wall insulation. So we can see that the thermal bridging impact has increased dramatically just by putting external wall insulation, proving that the greater the insulation layer, the more detrimental the thermal bridge effect. And the saving by using the thermal break solution had increased now to around about 17.5%. So this sort of wasn't exactly what we wanted to do. In lieu of trying to find a real balcony to test, which was the true goal, COVID hit. So we decided to try and make our own sort of hot box. There's a cheap solution and an expensive solution. The cheap being 2 sheds put together, and the expensive version being a container which would be insulated to the nines. And then I'll be able to put up my specimen between the hot and cold side and test it. Now, the budget was cut short, and the energy house came to the saving again, and they let me remove a window from the upstairs conditioning void, which is the neighbour to the actual energy house itself, so I could put my specimen in the wall. Now at the bottom you can see the preliminary models that I did, just to make sure that the flanking losses around the edges weren't affecting the 3-dimensional heat flow through the actual thermal break, which we want to monitor. So the bottom left shows you the schematic of the wall I chose, which we were aiming for about a U value of about 0.18. In the middle there, you've got about 110 mil of insulation. You've got a plywood facade with 2 air gaps. Now, and you can see the infrared imaging, external and internal, looking at the walls. Now, we cut a hole in this wall after a baseline test to put the steel through. The steel was then put in. We welded the steel up, so it was easy enough for me to change the thermal break variants from the external side. And we're going to test 6 variants, 3 materials and 2 thicknesses of each, 5 mil and 25 mil, and they're all Farrat breaks. So this is what it looks like at the minute, and this is where we're gathering data from. The steel beams being propped up on acro props, which are anchored to the wall and the floor, because I didn't realize how heavy this beam would be. So yeah, that took me by surprise a little bit. But this enables us to really look at what the breaks are doing. Aside from this, we are looking at using a real case study, but unfortunately we won't be able to get any heat through the actual embedded breaks that are put into this Energy House 2 construction until February next year. So this is a future work, but it allows us to actually monitor a real live case study of where these structural thermal breaks go by embedding sensors and tuning the models. Again, just trying to reduce the performance gaps between the as-built and the predicted energy performance. So I'll let Will finish up with where we're going in the future.
So I think this is quite interesting for us, really, because I suppose we see it as a sort of very much at regional policy. So what's going on in terms of what is going to be demanded by local authorities, city regions, with them all heading towards 2038, 2030, 2040 for zero carbon. And I think we're seeing less quick wins. So things like we're having to look at the detail a lot more. It's not just running around filling in cavities and putting loft insulation in. So we really need to start thinking a bit more heavily about the design from top to bottom, which Passive House helps us do. I think we're going to see a lot more measurement as sensors comes down, as comms comes down in terms of cost. People will want to see what things are actually doing, and really what things are actually doing is more important than how we've modeled them. And I think on the other side of things, and the thing we're very interested in is getting the skills and knowledge out there. I think people alluded to that, you know, the learning that we accumulate around these issues. I think that for me is if we're going to do anything at scale, is probably one of the most important things. Okay, I think that's us. Is that? Thanks, Joe.
Thanks very much, Will. Thanks, Joe. I'll quickly go over to Chris now, who I believe has his sound issues resolved now. This will be the last presentation before the final
so hopefully,
roundtable. Yeah.
Hopefully you can hear me now. I'm Chris Lister. I'm the value stream leader for thermal breaks in Farrat. As was alluded to, I started my life in structural engineering, realised I couldn't do the maths, moved into architecture, realised I couldn't do that either, and then ended up in product manufacture. So Farrat, here we are, engineers on a mission. We always like to think ourselves, I think, designers as being at the forefront of everything, but as was alluded to, some of these problems that we have been around for a long time. And I think that understanding that some of the problems that we see are not new. So in a Farrat, we have an interlinked stream. So we have both building acoustics and industrial being the basis on the company. We were founded 60 years ago, but we have a team that works across engineering, and that's where we find all our solutions from. Thermal breaks, which is the value stream I look after, we are very primarily concerned with construction of new build. We see retrofit, but a lot of the work we do, as seen in the details, is with steel frame. We see a lot of concrete work going on, but a lot of what we do is structural. The primary people we deal with are our steel work customers. So we spend a lot of time understanding what their world is, how they work, what they need from us, and making sure that we are answering all the questions that they put to us. We understand our specifying customers. They're a mixed bunch, and depending on who you come up against, they have some great ideas. We're quite happy to work with everyone and figure those out. We also understand that some of the things are unworkable, and really we should be able to, quite hand on heart, be able to tell people that isn't the case. We understand thermal performance. This is one of the cornerstones of what we do in Farrat. The work that we've just seen from Joe and from Will is that we want to understand to the deepest level what we do for thermal performance, because that is core to what we do. We also understand structural performance. We are engineers at heart, and we are trying to make sure that everything that we do stands up. So we have this ability to think both from a thermal point of view of the construction, the building envelope with the architects, and also with the structural engineers. And we understand it's a balancing act. We know that, you know, if something has got to stand up and it's made of steel, you know what, it's probably not very good at being an insulation. And equally, we understand that if you've got something fantastic at insulating, it's probably not going to have a structural performance to it. And that is where we sit. And that way we understand the compromise. We know that sometimes you can't do everything that you want, but we also understand that it doesn't have to be a total compromise in terms of its the aesthetic form of the building. And we understand that there are ways of making sure that those compromises don't define your building. So we spend a lot of time working solutions. We make products. We understand the role that we have in making something that is both affordable and capable of going into a building and not being missed and put in a skip and all these other things that happens on site. And that really comes from our detailed understanding of those elements. So the structure, you know, how these things go together, how something is going to be built, the sequence in which it's going to be built, you know, the materials that can be readily available on site and everything else that's going to go with it. That is one part of what we have to do. And then understanding the ultimate thermal requirements of that building, the comfort factors that have to go into it, the fact that you do not want to see a big black line of mold on your brand new penthouse. These are things that we understand, and therefore we're able to make informed decisions and make them into reality in terms of products. And this is not just something that has come about since, as we said, potentially 2002. We've been doing this for years. We're a third generation company. We have industrial engineering at our heart, and that comes through in everything that we do, whether that be building acoustics or thermal. So we have got to a stage where we understand optimum solutions. We are understanding that we are a key part of that design process. As I say, if you get us in early, we can give you a good feel for what will and what won't work based on our experience, same way has been seen in the real world, and then being able to really give answers that are trusted. So we have these exemplar performance levels that we know we can achieve, and we have all the backing of all those industry groups to be able to say, look, we know what we're talking about, and we'll tell you if we don't think it works. If you want to do something that you think will work, and we'll happily go along with you, and we'll happily help you achieve your goal. But in truth, we'll also tell you when we don't think that's a very good idea, and maybe you should look at a different way of doing it. It comes back to this idea that you are doing something safe in the knowledge it will work. We work in structures. Our products have to last the lifetime of the building. You need to make sure that when it goes in once and doesn't have to go in again, and that will work, because you don't get a second chance on some of these hidden structures. And that's the reality of these structural elements. So ultimately, we get to build buildings that we'd love to see. We push the building envelope, and from a Farrat point of view, we get to fulfill our mission statement, which is really delighting our customers. And that is really what we're all about at Farrat, making sure that we delight. So thank you very much for that.
That's great. So that concludes our presentation, and we can get back in. I know we're running a little bit over, but we to the extent that everybody's amenable to this, we can run on until 1 o'clock. And if anybody has to make their excuses, I completely understand. Yeah, I think we've had some fascinating presentations, going from the kind of historical context to some of the design considerations to the more practical considerations and the research that's being done in this area. I think it's extraordinary. We've come a long ways in the industry. I can't imagine being able to cover this kind of ground 5-10 years ago. With the extent of involvement and engagement that we have now. I'd just like to go back to the Q&A, because there's a bunch of questions now that have come through in Slido, and I want to try and whistle through them as quickly as we can, because we're not going to get through to all of them, because there's 23 questions as it stands, and I see some are spilling through into Zoom as well. So the second top question now, how seriously do you need to take thermal bridging from a structural perspective if you have good ventilation and air tightness?
You have to take it into account, full stop. There's no point of trying to design super energy efficient house and then have a massive thermal bridge on a steel connection coming out to support the balcony, especially that in terms of the cost. If you want to invest, you don't want to invest £500 per thermal break, you probably have to compromise with additional insulation somewhere else, or much better air tightness performance.
Would you expect if you have good ventilation and air tightness, but you have thermal bridging issues, would you expect it to just be an energy issue, or to potentially manifest itself in condensation?
I would say condensation. That will be our worry. We will not worry about probably energy loss. It's just worry at that point. If you have a super well insulated home and you have a steel beam going across, you worry that the client will come back to you and say, I've got a wet ceiling. And that's my reputation will drop down, because the first thing that the client has in his mind is that the plumbing is leaking or the roof is leaking. Nobody thinks about condensation. but in those much better and much better refurbished or insulated houses, the small thermal bridge will be even more visible, more apparent.
That was one of the things we're finding with the research with Joe, is that as we get better and better insulated envelopes, as we become better with planar values, as the psi values go up in window frames, the point connections, the chi values that we deal with become more and more apparent. You know, you've got, yes, we wholeheartedly try and avoid, you know, cold bridges and structures going through, but they do penetrate the envelope. So, you know, even if you've got great air sealing on the outside and great installation, that cold is on the inside, and any moisture, and particularly moisture that is in the structure itself, so, you know, the interstitial moisture, which is likely to be unseen completely, are the things that we're worried about. And as I say, they will become more apparent as you get better and better insulated envelopes.
I see Sarah's got her hand up, and actually I'm interested in her views on this. The question is interesting because from a policy context in Ireland, I know that there's a view from somebody at a high level, from a policy-making perspective, that if you that in retrofit, where you're trying to enable it to make deep retrofit affordable for the Mrs. Murphys or the Mrs. Smiths of this world, that you kind of need to compromise somewhere in order to make that happen, and that this that thermal bridging may be one of the areas where that compromise is acceptable. So Sarah, I'd love to your insights there. It'd be very interesting.
Yeah, I think you're absolutely right. I mean, with new build, I totally agree. There's no excuse. You deal with the thermal bridges. There's plenty of solutions out there. You know, you've got so many options. In retrofit, you know, people live in houses, they own houses, they rent houses. We've got to be pragmatic about this, and thinking about the bigger picture. We're not going to get every house to low energy. We're not going to get every house to passive house. So we're going to end up with thermal bridges. And as I said, I've got thermal bridges in my house. I can't afford to take up all the floors and go and deal with that thermal bridge around the edge. I had Cubot come in, spray under the floor, but they don't deal with the thermal bridges. But it's not an issue because it's well heated, it's well ventilated. We've got cavity wall insulation as well, which helps. So it's about thinking about the risks, I think, and educating the people that live in homes as to what the risks are when they do these insulation projects. I mean, obviously, yes, we'll always try and do the right thing, but if the budget's not there, sometimes we just have to be pragmatic about these things.
Do you think that the importance of thermal breaks, and more importantly, the integrity of a thermal envelope, are neglected in modern architectural courses? That's an interesting one. I suspect that's probably one that's best pitched at Mark, I would say.
Oh yeah, pick on me.
And anyone else wants to join in, feel free. Yeah.
I honestly think that, you know, there's an awful lot of courses where this is actually taken pretty seriously. I certainly know my wife would fail a lot of students for not considering it well, as she lectures more on the architectural technology course. No, I think it's something that's very much part of all programs, and I certainly know most of the courses in Dublin and Cork would have taken this seriously. And I think, you know, with people like John Moorhead coming in as external examiners, you'd be, you know, you wouldn't get away with it really. And we've had so many passive house designers per head of population in the Cork area that it has a serious influence on how our course is put together. I certainly know that the TU Dublin courses with Joseph Little as part of the team there, you know, they take it very seriously. I'm not sure what it's like in the UK. Maybe some of the other guys can and ladies can pop in on that one.
Yeah, I mean, at Salford, I suppose I would say it's patchy, even though we've got like a great research centre, and we do feed in. In the UK, I would say there's some real centres of excellence. You know, I think of like Leeds Beckett and Oxford Brookes, Loughborough, obviously, and obviously places in Scotland. I think Scotland seems more coordinated in some ways, and there's more sharing between the universities. But I would still say, you know, there's massive skill shortages still in this area. But yeah, I suppose 10 years ago, there were even more skill shortages. So at least it's emerging there. And I think there's an interest from undergraduates now to find out about this stuff in maybe a way they weren't 10 years ago.
Is there a sense that this is being addressed more in sort of a postgraduate level or in specific courses rather than as an integral part of undergraduate learning? And I'm just thinking, there's a journalist and medical doctor, Ben Goldacre, who would have had a big influence on the direction of our magazine. He wrote a white paper on evidence-based education a number of years ago in the UK, and talked about the advent of medical trials and and the advent of evidence-based medicine in the early 20th century, and how the authority figures in medicine at the time, in many cases, were very suspicious and mistrustful of this new approach, because it was a threat to their authority, as they perceived it. And he described it as the need to move from eminence-based medicine to evidence-based medicine. And I just wonder, in the context of some of the architectural schools, and I don't want to single them out for abuse because it's much broader than just that, of course, but you have authority figures in some cases who are teaching, it seems, I know that it's changing, but there's a sense that they may be teaching the same things that they've been espousing for, like passive solar design principles that are sort of 40, 50 years old, for instance, without subjecting it to scrutiny. Rob, you want to chip in there?
Yeah, sorry, this is quite an interesting topic, and I come across this quite a bit. Yeah, like Will said, it's quite patchy. Some places are great. We have some, even some graduates coming into our practice and they've already done the Passive House Designers course, and then there's others that wouldn't have done it or had the exposure to it. But one of the bigger issues is that a lot of the courses are being delivered in almost like a sandwich form nowadays. That they're trying to pack in BIM, they're trying to pack in building construction, they're trying to pack in the design side of things. So you also have the technology side. I went through Waterford Institute of Technology myself back, what was it, 2006 or so, like that sort of era. And we were very lucky. We had a lot of the lectures there were kind of all about the kind of the thermal bridging and all that, and still are. But now, we discuss with some of them now, and you kind of they're trying to find a balance now is the biggest issue, because to be market ready now, there's always a flip side. To be market ready as a graduate, is there a question? Do you need to be BIM ready, or do you have to use Revit and use do all the trickery and have a gradual understanding, or what's the how did it find a balance and fit that in 3 years or 4 years? I think the bigger, just from my own experience, my greatest learning has been, working on site, doing laboring, just getting back out. I'd almost say there needs to be more of a year out kind of experience phase. Like in some of our projects, we've even had, I think it was the Sutton Secondary School, the Passive House one, we had students working with the contractor on a year out, basically doing on-site learning, looking at all the Passive House evidencing, so a lot of that was opportunity for learning within the industry, so we need to create more platforms for that to happen and be less of a kind of a specialist thing and we'll all be expert generalists, I suppose, in a sense. So yeah, it's my view.
I think from my point of just on that point, and I'm reminded of listening to Maxwell Hutchinson looking at Mark's bow tie, talking about EWI. You just need to be able to understand, as passive houses, the core principles of what you need to do in your building. A core principle is don't have thermal bridges. Finding out how you do those thermal bridges in a particular building is something which is a specialist. Finding out what is the latest thing about that, but it's just one of the strings to your bow, alongside BIM, alongside being able to talk to people on a site. All these things that architecture teaches you when you come out of school, that you then only become good at 30, 40 years later as you've learned. But I think understanding that actually thermal bridging is not something you want, and being able to design out the first principles is pretty cool.
It's almost as if we still need to get to the situation where I'm minded of an architecture lecture I attended by a president of the Royal Institute of the Architects of Ireland, and we still have a Royal Institute, by the way, 100 years after independence, which is very curious. This is many years ago when we were, in the mid-noughties, early on in our publishing career, and there was a sense that green was being a lecture on green design, and there was a sense that he put across that that green was a color on a palette that an architect could choose. And I just wonder whether it's, rather than considering these things as fundamental principles for ensuring a building stands up and performs, properly, there's still that kind of consideration that it's something you can choose to address if you wish. I want to get on to other questions though. The next one was, how much damage, if any, can failure to tackle thermal bridging do to a building? Well, we've kind of covered this already. How much damage, if any, can failure to tackle thermal bridging do to a building and or to occupant health? I mean, well, I guess I'm thinking of any of our panelists who've done sort of expert witness work. I mean, and I know no one will be able to talk about sort of specifics here, but is anyone aware of cases where a building has catastrophically failed because of thermal bridging issues, or where they're contributory factors?
I've certainly come across, and it goes back to David's point about retrofitting on EWI, certainly where unknown problems have been caused by wrapping a layer around the outside of an existing building, which has then caused detriment to the occupants. And those occupants are at the whim of the landlord, and really they are the ones who are suffering. And so, yes, certainly I've been involved where things have had to be completely ripped off because they've just misunderstood where the dew point is going to be, and that's caused a problem where all the detailing around the eaves has caused more problems than it was set to solve, and then it's been rolled out across a housing stock of hundreds before someone has realised it. We do a lot of work in acoustics and structural vibration. We know exactly if that thing has failed the first time a train runs under it, or the first film is played. Thermal bridging, you don't realise that's happening until at least one thermal cycle. And so that's why understanding it at the level we do with Salford gives us a much better chance of saying, whoa, you've got a problem there, do this. And that's what we spend a lot of time doing, is just saying, look, you really need to think about this, or completely design it out.
It's a very interesting point, because we may end up, I'm thinking of some of the woofy simulations that people like Joseph Little would have done for our magazine many years ago, and showing over how problems can gradually increase. They may not become manifest for 3 or 4 years in some cases after the building or the retrofit work has been completed. I don't want to put anybody in a sticky position to divulge details that might be too close to contentious buildings. So I'll go on to the next question. Here we go. Are you able to suggest the best ways to form or thermally separate parapets to improve PHBP calculations? Any takers?
Yeah, again, it's one that we've been dealing with quite a bit recently, especially when it comes to steel frame. The biggest issue is the context. So there's little information in there, but it's to step back from it and look at what are the pieces that are bridging and how we can get those out of that space. Then working, I think this is where the collaboration with the structural engineer and the people and the contractors as well, because procurement becomes a big issue. So if you can imagine a steel parapet, if you're separating it and putting thermal breaks in, for example, responsibility of who's going to apply those things on site. Is it going to be the steel worker, or is it going to be someone else comes back in and does it? These have significant delays on the actual delivery when it comes to it on site. That's where your weeks and your 2 weeks start to come into play, because of just the information wasn't clear very early. So I know I'm not answering the question really in a sense that because you kind of need to see the context in the drawing, but there are ways we can do it, to remove that linear break or linear thermal bridge. Yeah, and by doing that, there are improvements as well, where you're saving on insulation in other ways later down the line, by an application onto that parapet. Yeah, so I think the biggest thing is the collaboration with the structural engineer early, and if you can, the contractor and subcontractor.
Fantastic. I'll move on again. This is interesting. Should there be up-to-date guidance on details to limit thermal bridging in a government-approved document or supporting publication? I'm presuming the person raising this question is talking about more up to date version of. I mean, in Ireland we have, well, both countries have what they call ACDs, I gather. In Ireland, the A stands for acceptable. Seems to portray a complete dearth of ambition. You know, it's the least bad, or the just about the tolerable, you know, approach. Whereas in the UK, I think it's accredited, if that's correct. You know, and I can tell you in an Irish context, looking at the data on new homes, we have the sum total of data on new homes through our energy rating system. Approximately 70% of new homes built to our nearly zero energy building standard are using a default Y factor of 0.08, which is attributed with using the acceptable construction details. John, you might have views on this, I would have thought. John Moorhead, from your perspective.
Yeah, can you hear me?
Yeah.
Yeah, it's incredible, really, when you think that use of the 0.08 Y factor hasn't changed since the 2011 regs, and we're now using, they're being used, as you say, for 75% thereabouts of all buildings meeting NZEB, and I think it's reflecting the use of offsetting. In other words, screw the building envelope performance, screw the fact that you're doubling the effective thermal losses through the walls that your client is spending a fortune on, but let's whack in a bit of PV and whack in a bit of heat pump, and we'll be fine. We'll meet our asset rating target that we need to meet. And I think, and we've discussed this, Jeff, at length, I think COVID has identified a lot of this, you know, the failure in this system, in that people are now working from home. They're now not, you know, in Ireland, buildings are rated based on being heated 8 hours a day. That's it, 7 days a week. So 56 hours, you know, a week they're being heated, and that's where all the losses are being generated from. Whereas people are now 24/7 at home, working from home, and there's, I think there's a real issue here, that and incoming comfort standards, where, you know, our energy losses aren't taking account of basic levels of comfort either. We need to really get our act in gear on that if we're going to meet the intent of the Energy Performance of Buildings Directive, at least. I think it's a real problem, and goes back to, say, colleges and universities everywhere, where thermal bridges and studies and thermal bridges were maybe for nerds, and you had this sort of siloized thinking that they weren't for them. Now, I think that's changing rapidly, I think the last 3 or 4 years. But, you know, if you looked at the last 10 years of naval architecture and say, you know, which is, again, it's performance driven, much easier metrics to see. You just look at the America's Cup last year, and just look at the beauty of the boats and how they're built, and the adoption of technologies in that industry, and then step back and look at the architectural or construction industry. We're getting there, but we're very slow, very, very slow. And I think it's failures like, okay, when the rudders failed in, was the 1979 Fastnet, when they started using carbon in naval, you know, the leading naval architects, it was dramatic, everyone saw it, but we're not going to see the failures due to not addressing thermal bridging in NZ buildings for maybe 3 or 4 years, and then we really will see it. We're going to see condensation issues within fabric that are going to cause huge damage. So it's really disappointing that it's not being pushed, and maybe it should be mandatory that thermal bridges are addressed, and that you can't use these mediocre default Y factor levels.
Well, I see one of the attendees has referenced the fact that the ACDs in the UK are going to be dropped from next year, if I understand correctly. I should know this. No longer used for new homes, and from next year, and the Y value will go to 0.20 for the Y factor, which would be pretty extraordinary if that's the case. I just wonder whether it always struck me that a more elegant or simpler solution. Because the issue in Ireland was always that the building standards section of the department just didn't have the resources at the time to get it updated, or that was the arguments you would hear from them. But surely, you know, proprietary thermal brake suppliers and build system suppliers. Why not just open it up to enable them to have to publish their details into a shared database, so that you've got a resource. If they're willing to pay for it because it's good for their product, then enable that as the kind of workaround, I would have thought.
I certainly think, Jeff, that, if like touching on a few questions there on what you just said, like the idea of actually having a number of prototypes or tested standards across different typologies, especially in a retrofit context, would certainly help the industry, because there are certain barriers in both, like what Robert was talking about, in educating students to be ready as graduates for industry in what you choose to teach them. And then you're kind of saying, okay, well, what are the barriers to that? If I was going to try and teach all of these students Scytherm, for example, at $4,000 a seat, that could be a barrier to actually educating them. And then within architecture schools, the prevalence of actually teaching people new build as opposed to retrofit, and perhaps if there was more of a focus on retrofit, we would have we would value thermal bridges an awful lot more. And I really do think, Passive House does a great job in showing the exemplars of retrofits of different typologies. Wouldn't it be great to have, I suppose, a one-stop shop where we could say, right, I'm retrofitting a 1950s mid-terraced concrete house. What should I do? Let's go over there, take a look at 5 different exemplars which have the details, which I suppose have been tested and tracked over time to show did these work. And at least I, as a client owning a building like that, would have a starting point, because we would have to accept that a lot of these barriers are also the skill sets within architectural practices to actually analyze these details. So that's why they're going back to the ACDs, because they don't have the skill sets. And we've now said that, okay, well, if you're going to do thermal bridging analysis, you actually have to go to a licensed contractor to do that, which is really kind of selling out the fact that, like, kind of, we don't have these skill sets within practices, and we're saying, no, these are going to be subbed out. And I suppose any of us who have been involved in deep retrofit would understand how much time and cost it involves to do all of these things that are extra over and above what your architectural fee is.
Absolutely. I don't know if anyone wants to give in. We're over 1 o'clock now. I'm happy to continue on for another few minutes, but feel free if anybody wants to. I think Sarah Price has to leave, but if anybody else has to leave now, now, Nick, you look like you're making your apologies, yeah, and Ruth as well. Okay, yeah, thank you so much. Look, perhaps I'm happy to keep going for 5 or 10 minutes more, if that's okay with anyone. But Nick and anyone else who has to leave, Ruth, yeah, feel free. And we'll try and get through some more questions. But are any of our other panelists okay to hang around for another 5 or 10 minutes? Yeah. Okay, great. Thanks, guys.
Yep.
I just want to get through a couple more questions. Should you calculate every thermal bridge? Yes, no, or estimates okay in some cases? What are the rules of thumb? Anyone fancy taking that on?
I think there's the reality and there's the the ideal. Yes, ideally you would calculate the thermal, but it's the idea that you had already decided to take out as many obvious thermal bridges as possible. But certainly in our case, in point thermal bridges in structures, you need to know an awful lot about that building, and you need to be able to understand the detail and how all those materials interact before it makes a material difference. So, we have got to the stage where we've been having a detail that has been refined, and we know it's going to repeat it over 1,000 balconies, and so therefore it's worth doing it and worth tweaking it to make sure that you can get a better performance. Equally, where you've got multiple, so you've got lots and lots of connections in a cladding facade, and you can refine that detail so that when you implement that detail 1,000 times, it's as good as it possibly can be. So therefore it's worth doing that one. But where in a lot of situations you have a one-off detail that will only repeat once or twice, the work that we've done tells us, you know what, there's a law of diminishing returns. As long as you've done something, that gets you a good internal temperature factor, critical internal temperature factor, yeah, that's it. Move on, spend your money on something else.
Should you take particular attention to rooms where, for instance, bedrooms where you may have lower temperatures, or places where you may have lower air movement in a room, for instance? You know,
I think the biggest one where we find it, I mean, where you know your building is going to have a high humidity, so a brewery, a swimming pool or something like that, then you've got, you know there's going to be a problem, so spend more time there. A lot of time when you know that actually the surrounding wall above a balcony, the majority of it isn't going to be lovely, thick, warm, insulated wall. It's going to be a double glazed unit with potentially an issue around the frame. Have a look at that detail. If that detail repeats, 100 times across your building, do some work on it. If it's once, make sure that you do something on it. But you're going to have other problems somewhere else. Again, it's where do you spend your time and your money and resource.
Absolutely. Okay, we'll maybe take a couple more questions unless people want to chip in with anything else specifically. Projects which use pile foundations, are the piles significant for Passive House? Thinking about insulating pile caps plus a foam collar around the top, 1 meter. Overkill? Anyone any views on that?
I've done that. It is a very painful way forward. So when we were working inside and looking at it, for us it felt like overkill, but we did it. But I have to say that in terms of raft foundation, because this was a piles followed with raft foundation, and then it was a heavy soil, clay soil. We also had to have a compaction zone, which supposed to collapse. And then when this was supposed to collapse, the insulation started moving around. It was really, really wobbly and very difficult to work with. And at the end, after pouring the concrete slab, we realized we are off by 30 mil on the levels. So we had to go with additional screeds, and yeah, it wasn't a pleasant experience.
Yeah, okay, that's very useful practical insights there.
We had one, Jeff, recently as well. We had 70 mini piles under a building, very poor ground conditions, and looked at the thermal bridges, calculated them, and it was actually quite significant. It was onto shaly rock, so really didn't help us. And in the end, we capped the whole lot of them with a slab, and we built a raft basically above that. That's how we got around it. But there's times you come up against those things and you have to make a call, because the project has to be deliverable, safe and cost effective. And sometimes fiddling with all those potential issues, it was better to just try to sort it out with a simple engineering solution, and that's what we ended up doing.
Okay, great. Couple of last ones. Why is all thermal bridging software clunky and rubbish? We could probably leave that one. Hopefully, as it becomes more mainstream, we'll start to see user experience being more of a consideration in software design. But I know that that's an issue that's not. I say, as somebody who's constantly befuddled by tech, as this event shows clearly, I'd say it's in fairness, in my case, it's probably more of a reflection of me than the software, but I think it's not just restricted to thermal bridging software. Do you think the presence of the ACDs leads to very defensive design and construction specifications? That's I think a very useful question. Anyone want to take that up? I think John's already tackled that to some extent by saying, moving away to you're looking for technical solutions. But there's a risk, I suppose, which I think again you probably addressed, John, that it stops people being ambitious with the fabric and making errors in that way. what else have we got? Just loving to see, and if you look in the chat section, so many very nice comments, which I'm very, very appreciative of, and I'm very thankful to all of our panelists for giving some extraordinary insights. If anyone else has anything particularly they'd like to raise, knock yourselves out. But I think we probably, yeah, Raphael, go first.
Yeah, very quickly. Can I just add something for architects working in educational areas? What I'm finding is that understanding about what material, in terms of insulation materials, what they are, how you can use them, how you can fix them. Architects lack a bit of experience, especially the young architects who come to our sites. So we would have somebody who wants to use foam glass, which is really brittle material, and try to put the screws through it. What I would love to have is 1 hour at the university where you pile all the insulation materials on the front of you and say, this one you can hit and it will not break. And this one you can hit it slightly and will fall apart. This one can take load, this one cannot take load. Just some basic understanding on material of the insulation, that would be fantastic.
Yeah, with that kind of practical consideration. Mark, you want to chip in with something? Or is he just
no, I'm just agreeing, and I'm hoping Raphael is going to come over and do a presentation for us.
It's fantastic.
I already have all the insulation materials in the warehouse.
Well, you got a lot of anger to vent as well. Yeah, exactly. Tara, if you want to
yeah, I would just say about insulation materials, because it's like the manufacturers provide loading capacities, but we don't design to those loading capacities because we've got to consider for long-term shrinkage and creep. So they often come down to about a third of what they are. And we end up in quite a lot of arguments with architects because they kind of go, but it works because it's got, but there's a kind of like the science has to be a bit more understood, I think, in that as well. Yeah.
Wow, that's extraordinary. Yeah. And again,
yeah, so a 300 Newton is, we designed for about 90. Yeah, that's where the point for us is. Yeah. And I think there's quite a few engineers don't realize that. And there's probably quite a lot of stuff being built wrong out there.
Oh God.
I think that, I mean, I think that is I mean, it's a point that we would reinforce. We spend an awful lot of time testing and making sure that we are within safe limits and making sure that we publish design, basically design loadings as opposed to characteristic values, because we know that these things, and we do an awful lot of compressive, long-term compressive creep testing, because there's a lot of materials out there that say they will work, but when you actually do it, in real life and try and keep it in there for 50 years, it doesn't. It's a very similar situation with fire nowadays. Fire is very much the case, is very much there. There's an awful lot of stuff out there that we would not be happy putting our name to. We spend an awful lot of time making sure we can sleep safely at night. So again, it's making sure that you choose the right people to go with all these things.
Well, we only have to look back to the horrors of the Grenfell inquiry evidence, that's been played out over the last few months to see as well the concerns you can have. And so, I mean, I guess where you have situations where manufacturers are not necessarily being, honest with the information they're sharing, or not, it's all built on sand in those cases. So hence the need probably for more. Maybe there are in some cases legitimate causes for defensive specifications, where we try not to sail too close to the wind. To go back to your sailing analogy, John. John had a very interesting question there. Should the FRSI temperature factor be taken at the airtight layer rather than the FRSI is essentially the surface temperature is what it's described as in the case of new homes, right? Rather than the internal surface. Potential for mold in service cavities is real. So I think that's a fascinating insight.
Yeah. Do you mind if I jump in on this? Because it's only something I was looking at last week, John.
Yeah.
I know all our guidance was say, the internal surface of the high risk point and the psi value, but like yourself, as you just raised that question, I would always go back to the point of the air tightness line, more so probably the vapor barrier in particular, because that's a surface cavity, although it's not a what would you call it, a heated space. Effectively, it's still evidently kind of exposed to some change in airs. Like, it's not airtight effectively, air exchange, but yeah, I personally think that's a good practice to always look back into that point, you know, where your where the vapor line is and the air tightness line. And also the biggest thing is also the context of the construction. Steel, SFS, definitely, you know, they're really highly conductive materials. Timber, you'll probably find that due to the conductivity and the how they're able to manage these things a lot better. Yeah, and then concrete and block work as well. There's kind of a gradual kind of inertia in the materials as well. But no, it's really relevant question, especially at the moment where we're trying to insulate things so well and achieve highly insulated structures using, what would you call it, business as usual type methodologies, and just refine and gradually bring the industry along rather than shock changes, you know. But yeah, really valid question.
Fantastic. I see that there's other questions. Just 1 second, Raphael, that a number of people have asked, which through the chat, which I'm not going to be able to find. Raphael, you've got to head off. That's right. Yeah. Okay. You know what? I think probably it does make sense to wrap up now, because we're going on for 2.25 hours. We're long into, you know, past the extra time and into penalty shootout territory to go into the Euro 2020 metaphors. But look, thank you so much to everyone. I'm so sorry for any questions that we've missed. Please understand that if I haven't taken any decisions not to raise questions on purpose. It's you know, wherever there's a choice between something sinister in my motivations and incompetence, it'll always be the incompetence that wins out. Okay, I promise. So, and not that there's not much comfort to be had in that, but look, thank you so much to all of our speakers. Thanks. You know, I've certainly learned a lot. I'm thrilled to see that people are talking about having further roundtables. Hopefully we can work out how to make that happen. I just like to thank Farrat for sponsoring this, all the speakers for giving so much of their time, and to all the attendees for the patience of sitting through this and all of the technical foibles and meandering from me as well. So on that note, thank you to everyone. I'll no doubt be speaking to you all soon, and we'll then be notifying everyone after the event with hopefully within a day or so. There'll be recordings circulating. Thank you.
Thanks.
Thanks.
Take care,
everyone.
Cheers.
Thank you.
Good to see you all.
Bye-bye.